Okay, I'm starting the recording. We are now going from the ebook, and I wanted to bring up the menu because I wanted to show you where this is, the polar coordinates. So down in the ebook, you have what are called appendices. And if you click on the appendices, okay, so of course you have to click on the little menu here, and you'll find polar coordinates. And then here we go, we're at polar coordinates. So let's talk about this. So polar coordinates offer an alternative way of locating points in a plane. So what you're used to seeing are Cartesian coordinates, X, Y coordinates. Polar coordinates are a little different. They're a different way to locate a point in a plane than a Cartesian coordinate is, and they're useful because certain types of regions and curves, polar coordinates provide very simple descriptions and equations. The principal applications of this idea occur in multivariable calculus, okay, which you'll, if you take Math 280, which by the way I'm teaching in the fall or in the spring, you'll have the evaluation of like double integrals and all kinds of cool stuff. So let's go down here a little bit and take a look here at a polar coordinate. So in figure one, you have what's called a polar coordinate. So you see that point P, instead of an X and a Y, you have an R and a theta. So the theta is the angle measured from the positive x-axis. So just like in trigonometry, you measure all angles from the positive x-axis. That's theta. So if you measure some angle theta, and then from the origin you move out some radius r, you reach a point P in the xy plane. The polar coordinates r and theta are locate that point in the plane. Okay, so like for example, if I go to the whiteboard here, okay, I'll go to the whiteboard, and let's say you had something like this. One moment, got to find my stuff. Here it is. Okay, so you have an x and a y axis. Okay, and let's say, for instance, that you go out an angle of theta, which is pi over 4, and then from the origin, you move out a radius of 2. The point P here, the point P, would have polar coordinates of 2, comma, pi over 4. Okay, that is a polar coordinate. Okay. Now we could find the Cartesian coordinates of that point, but let's just study the polar coordinates now. Now look at what else we can do here. We could start at the positive x-axis and go around 360 degrees plus pi over 4. In other words, this theta would be 2 pi plus pi over 4, which is 9 pi over 4, because 2 pi is the same as 8 pi divided by 4. And so another polar coordinate here for this point here in the xy plane, another polar coordinate would be 2, comma, 9 pi over 4. Unlike Cartesian coordinates, again, Cartesian coordinates are xy coordinates. Unlike Cartesian coordinates, you can have a point in the xy plane and have an infinite number of polar coordinates describe that point. Now I'll show you one more. I'll show you one more. Let's say, let me just draw this here. And let's say from the positive x-axis, you do an angle of 5 pi over 4. And let me just, just kind of, pi over 4 is 45 degrees. 9 pi over 4 is, oh gosh, 405 degrees. And 5 pi over 4 is 225 degrees. So how many of you like thinking in terms of degrees when doing trig? I like thinking in terms of degrees and then converting to radians. But so, okay, we go out 225 degrees. Another polar coordinate that for this point here is going to be, well, theta would be 5 pi over 4, and the radius would be -2. You see, if a negative radius, you can have a negative radius in polar coordinates. Negative radius means that you're looking, I want to do this the right way, you're looking in the direction here of 225 degrees, but you walk backwards, you go backwards 2 units. And so you can have the polar coordinate -2 comma 5 pi over 4 also as another representation of that red point in that red point P in the xy plane. Are there any questions on that? Kind of a quick introduction to polar coordinates here. All right, well, if we're good with that, let's go back to the book. Wait, hold on. So Mario, if I go back to that blackboard there, the fourth quadrant, you could like get an angle in the fourth quadrant. This is the fourth quadrant here. You could not get an angle in the fourth quadrant and have it work. Yeah, it wouldn't work. Good question. Good question. Okay, very good. Very good. So in the book here, hold on, Ange had a question. One moment, Ange. So Ange, we could certainly get a formula to, like a formula in terms of K, like some integer K, and then get a general formula for that. I don't want to get, I see you quoted something in the chat window. I want to be careful before saying that's right, because it's easy to make a mistake on that kind of thing. I think for your homework, you're going to be given sort of more specific angles. But I know what you're thinking there. I know what you're thinking. So, okay. So in example 1, they want you to plot these 4 polar coordinates. And the pictures are below. So the first coordinate is 1 comma 5 pi over 4, which is an angle of 225 degrees. And then you move out a positive radius 1. That's the first picture in figure 3. The second polar coordinate is 2 comma 3 over 3 pi. You move out 3 times pi. That's 3 times 180 degrees. That's 540 degrees. And then you move out a positive radius 2, and you get the polar coordinate in the second picture. For C, you have a polar coordinate of radius of positive radius 2 and an angle negative 2 pi over 3. So now negative angles, you don't go counterclockwise, but you go clockwise. Well, pi over 3 is 60 degrees, so negative 2 times pi over 3 is negative 120 degrees. So you go clockwise 120 degrees from the positive x-axis, and then you move forward a radius of 2. That gets you the third picture. And then finally, the fourth picture, you have a negative radius of 3, and then 3 times pi over 4. Well, 3 times pi over 4, that's 3 times 45 degrees. That's 135 degrees. So you're looking in the second quadrant, but you move backwards 3 units. And so the polar coordinate actually ends up being in the fourth quadrant. Okay, so that's just an example of plotting some polar coordinates. And in WebAssign, you'll have problems where they'll give you a polar coordinate and they'll say, all right, which of the 4 graphs is correct? And so you have to, that's multiple choice. You have to be careful, but you just kind of carefully do the problem. Okay, now something that we like to do oftentimes is convert from polar coordinates to rectangular coordinates, or from rectangular coordinates to polar coordinates. So we need equations that relate Cartesian coordinates and polar coordinates. Well, this is really something you learned in trigonometry. Okay, certainly you know that the cosine of theta is x over r, x over the radius, and the sine of theta is y divided by the radius. And so then in formula 1 there, x is r times cosine of theta, and y equals r times the sine of theta. And of course, we're talking in the context always of a right angle, and so those are two very. How many remember those formulas from their trigonometry days? X equals r cosine theta and y equals r sine theta. Sure, Ange remembers that. You couldn't miss it, right? You couldn't miss it. Okay, well, and then let's not forget that r squared equals x squared plus y squared, and tangent of theta is equal to y over x. So these formulas will allow you to do problems like example 2. Example 2 from appendix H.1 says convert the polar coordinate 2 comma pi over 3 to a Cartesian coordinate. That's an xy coordinate. So, well, x equals r cosine theta and y equals r sine theta. So we just plug in the 2 for the radius, and the angle is pi over 3. And so you'll get Cartesian coordinates of 1 comma root 3. Are there any questions on that? All right. Well, we can also go the other way. We can take a Cartesian coordinate and write it in terms of polar coordinates. And example 3 shows you how to do that. So I think that's fairly simple. I want to move on a little bit here. Let's talk here about example 4. What curve is represented by the polar equation r equals 2? So just like equations in well, if in polar coordinates, so in Cartesian coordinates you have functions of x, so you have an x and a y. With polar coordinates you have radius as a function of theta typically. Well, if r equals 2, you're saying theta can be anything. Well, r equals 2 would represent that purple circle there in the picture in figure 6. That's a circle, r equals 2. And you can draw other circles. Now, you might wonder, well, gee, that a circle of radius of 2 centered at the origin, I'm used to that being of having a Cartesian equation. Well, let's talk about that. Let's talk about that. So if you have r equals 2, this means then that r squared is equal to 4, but r squared is x squared plus y squared equals 4, right? The radius, I've got to be a little careful here. Yeah, r squared equals x squared plus y squared. So you're used to this kind of equation, right? That's an equation of a circle with center 0, 0. And radius 2. Okay. Well, so this is in terms of Cartesian. That's a Cartesian equation for the circle centered at 0, 0 and radius 2. But for polar coordinates, the equation is r equals 2. It's really like two different languages, but they represent the same thing. Now, which is an easier equation? R equals 2 or x squared plus y squared equals 4? Which equation is essentially easier? The polar equation? Right, r equals 2. This is easier. That's right, Ange. And that's because polar coordinates work very well when you have circles. They work very well when you have circles. All right, are there any questions before I continue on here? Okay, well let's work through a few more examples here. So example 5 wants you to sketch the polar curve theta equals 1. Okay, and that's going to be a straight line passing through the origin. Now let's go to the whiteboard and look at that. Let's go to the whiteboard and look at this example 5. Okay, so for that, if I draw a y-axis and an x-axis, here's the origin. Okay, I'm going to draw, so like, okay, what would 1 equal? Well, 1 is equal to 1 times 180 degrees. That's why I hate this. It always has that 5-point font. It's just a little too big to like things to be very clear. So hold on here. Right, so 1 is a radian measure for an angle. That's going to equal 1 times 180 degrees over pi radians. And that's going to be 180 divided by pi is about 57.3 degrees. So I can draw angles that are about 57.3 degrees, right? Theta equals 1, and I can put points at those right there. So maybe this point here, might have the coordinate 1, 1, because radius of 1, right? And then if I were to go out like further, if I were to go out maybe another radius of 1, well, this point here would have polar coordinate 2, 1. See that? R theta. And if I were to go here, well, let's just keep it. Let's just keep it simple. You can see that if we look at this line segment, every angle, every point on that line segment has theta equals 1. Now, this point here, incidentally, would have polar coordinates -1, 1, right? Because you're going backwards. You're looking in like here at the origin, and you're looking in the direction of 57 degrees in the first quadrant, but you're moving backwards 1 unit. So that has polar coordinates -1, 1. So this theta equals 1 is actually, it's sort of amazing. It's a line. It's that line in two-dimensional space. And so that's how we arrive at this answer. Now we can do something a little more interesting. I mean, well, that's interesting, but let's look at something like this. The polar equation R equals 2 cosine theta. All right, so R equals 2 cosine theta. So just like any time you're learning how to graph functions, like if you had a function f of x, like y equals x squared, that's a parabola, right, passing through the origin. And when you learn to graph the parabola y equals x squared, what did you do? You made a table of values. You picked some nice x values and then found some nice y values for those x values. I mean, well, you picked nice x values, you got the y values for those nice x values, and then you plotted the coordinates, and you were able to graph the picture of the parabola y equals x squared. Well, if we have R equals 2 cosine theta, theta is the independent variable, R is the dependent variable. So I'm gonna, you see there in figure 8, this by the way is example 6 that we're doing from appendix H.1. Figure 8, they pick some nice values for theta, and then they find the radii for those values. So all those angles there for theta are nice angles where you can nicely compute the radius. So like, for instance, when theta equals 0, R equals 2 times the cosine of 0, and that equals 2 times 1, which is 2. So you see there in the graph to the right, you start at 2, 0. That's a polar coordinate. When theta equals pi over 6, or 30 degrees, well, radius is 2 times the cosine of 30 degrees, that equals 2 times root 3 over 2. That's going to be root 3. So root 3 comma pi over 6 is the next point that they draw on that circle. And if theta is pi over 4, cosine of pi over 4 is root 2 over 2. So the radius is 2 times root 2 over 2. That's root 2. So there's the third point, root with polar coordinate root 2 pi over 4. And you keep doing this. Now, when you get to pi over 2, r equals 0. So you're at the origin, but you're looking up 90 degrees. But then when you get to 2 pi over 3, that's 120 degrees. The cosine of 120 degrees is negative a half. Remember, 120 degrees is in the second quadrant, so cosine is negative there. 2 times the cosine of negative 120 degrees is 2 times negative a half, and that's equals negative 1. So if you look in the direction of 120 degrees, but move backwards 1 unit, you arrive at the point negative 1, 2 pi over 3 at that polar coordinate. You can see it there in the picture. All right, and if you keep plotting the points, you're going to trace out a circle. You're going to trace out a circle. Okay, so now, are there any questions on that? We're going to have technology help us graph these polar graphs, but are there any questions? Okay, well now you notice that circle is not centered at the origin. So can we get the graph of r equals 2 cosine theta? Can we get the graph of that circle? Can we get that function and express it as in a Cartesian equation? The answer is yes, we can. Because if we have here, okay, we have r equals 2 cosine theta. Well, that means r equals 2 times x over r. Cosine of theta is x over r. So r equals 2x divided by r. And what I can do is I can multiply by r on both sides. And then I'm going to get r squared equals 2x. Now r squared is x squared plus y squared. So you have x squared plus y squared equals 2x. Okay, hopefully we're good so far. And this is talked about in the book too, under example 6, in appendix H.1. But let me just, kind of add a few more details. So I can write the equation as x squared minus 2x plus y squared equals 0. And I want to get this in the normal form for a circle, where I can identify the radius in the center. So I'm going to do something called completing the square. And I'm going to add 1 to both sides of the equation. This here will become then x minus 1 squared. So you have x minus 1 squared plus y minus 0 squared equals 1. So your circle has center 1, 0 and radius of 1. 1 is the same as 1 squared, right? So that's what you're used to doing, okay? So you see, you can always take a polar equation. Well, sometimes you can take a polar equation and express it as the corresponding Cartesian equation. And this one you're more familiar with, the Cartesian equation, right? But now you're going to get used to polar equations too. Some courses, I'm told, in engineering, they use polar equations like exclusively for the course, because like there's a lot of movement in circles, centripetal forces, and so forth. I had a student that took a class a number of years ago. I think it was at Georgia Tech, and he said his class, the math was that they used a lot of polar coordinates. But if we go back to the example in Figure 8, you can see that circle is centered at 1, 0 and has radius 1. Pretty cool, huh? Pretty cool. I'll mention too that you can graph in Desmos as well, polar equations. So this r equals 2 cosine theta. If I wanted to graph that in Desmos, let me just bring up Desmos. Hold on, I don't want that. I'm kind of in a, I want to get one example in here. Let me just try to get into Desmos. Okay, can you all see Desmos here okay? Give me a thumbs up if Desmos is showing up okay for you. Very good. Thank you, Taj. Thank you, David. So look, R equals 2 cosine of theta. See? There is your polar graph. So with Desmos, you have to use normally R and theta. When you do that, Desmos will recognize that you're typing in a polar equation. But you know, if this one's a little boring for you, hey, let me do this. Watch this. I'm going to put here a 2. Hey, how about that? How about that? 4-leaf rose. How many think that's pretty cool? Yeah, David's liking that. And you know, we're actually going to learn how to find the area of those petals, of all the 4 petals, and the area inside those 4 petals. That's something we'll learn next week. But yeah, so you can certainly use Desmos to help you do polar graphs. All right, so let me do one thing here. I want to get one example quickly in here. Okay, so just go ahead and copy this down. And I'll go, and we'll get to the answer very quickly here. Okay, so what we want to do here is, so you'll see problems similar to this in WebAssign. We want to find polar coordinates of the point with these Cartesian coordinates, -1, √3. And for A, we want the radius being positive and theta to be between 0 and 2 pi. And for B, we're going to allow the radius to be negative and theta is between 0 and 2 pi. So for this problem, of course, they have to restrict theta because, as you know, polar coordinates, there are an infinite number of polar coordinates that would work here. So I always find it best to draw a picture, of the situation. So I'm going to draw -1 √3, and that'll be in the second quadrant. And then, of course, we have to make use of our knowledge of appropriate right triangles. So in the solution here, I've drawn -1 √3 up here. There's the point. And of course, we have a 30, 60, 90 triangle here with reference angle of 60 degrees. Pi over 3 is 60 degrees. Okay, so you've done this in trigonometry. You know how this works. This side here would be √3. This side here would be -1, and 30, 60, 90 triangle. This reference angle here opens up to the larger side, so it's got to be the 60 degrees. I mean, you've done this before. So look, 2 pi over 3 is equal to 120 degrees. And if you go from the positive x-axis 120 degrees and move forward 2 units, you arrive at point P. So that'll be the answer to A. Now for the answer to B, you have to go from 2 pi over 3 and you have to go out another 180 degrees. So this is this angle here. 2 pi over 3 plus pi is 5 pi over 3 because pi is 3 pi divided by 3. So that's going to be your answer for part B. Okay, so I always find it helpful to draw pictures, and we always note that there are an infinite number of polar coordinates for this point. There are an infinite number of polar coordinates for this point, and these are, a few more examples. Are there any? I'm going to make another comment, but are there any questions regarding the picture here or what you're seeing? Okay, I tried to label a lot of things to help you. Now I want to make another comment. So in section H.1 in the WebAssign homework, you can see problems, for instance, where like they'll ask you the same kind of questions. They'll give you like a Cartesian coordinate -1, +3, and they'll ask you the same kind of question. Find some polar coordinates for that Cartesian coordinate. But the problem is -1, 3 is not one of them. It's not like a nice point. You're not going to get a nice angle like 60 degrees or 30 degrees or 45 degrees. So you can certainly, so what I'm trying to say is, for that kind of problem, if you're going to work ahead, if you're going to work on section H.1, that polar coordinate assignment, you can for now skip the kind of problems where they want you to find, polar coordinates for a coordinate like -1, 3, where the angle's not nice, because I'm going to do one like that on next Tuesday. Okay, but the rest of it you should be good with H.1. The homework there. Of course, first you have to worry about sections 8.7, which is due Sunday, and 8.8, which is due Tuesday, right? All right, are there any questions before I stop the recording? Okay, excellent, excellent. Well, sounds like you're all good here, so I will stop the recording.